Welcome to our channel. Today we're diving into the fascinating process of how planets form in space. From tiny grains of dust to massive gas giants, let's break it down step by step. We're about to embark on a cosmic journey, a tale of celestial choreography and the awe-inspiring forces that shape our universe. Get ready to explore the vast clouds of gas and dust where stars ignite, and witness the birth of planetary systems, including our own. Fasten your seatbelts, space explorers, as we unravel the mysteries of planet formation and uncover the incredible processes that led to the world we call home. Our story begins within a nebula, an immense cloud of gas and dust scattered across the vast canvas of space. These cosmic clouds, often remnants of past stars, hold the ingredients for new beginnings. Imagine a nebula so vast, it would take light itself thousands of years to journey from one side to the other. Within these swirling clouds, gravity acts as a sculptor, gently pulling particles together. Over eons, regions within the nebula become denser, their gravitational pull intensifying. Like a spinning figure skater drawing in their arms, this collapsing cloud begins to rotate faster and faster. At the heart of this swirling vortex, temperature and pressure skyrocket. Atoms, once content to drift through the void, are now forced to collide with unimaginable force. And then, a spark. A star is born, a brilliant beacon illuminating the surrounding darkness. This newborn star, a protostar, is a celestial furnace, radiating heat and light. But the story doesn't end there. Surrounding this young star is a swirling disk of leftover gas and dust, the protoplanetary disk. This disk, a cosmic nursery, is where planets will take shape. Think of this disk as a cosmic pizza dough, constantly spinning and flattening. Within this disk, the seeds of planets are sown. Every planet, every moon, every asteroid and comet in a solar system, all originate from this swirling disk of gas and dust. Our own solar system, with its inner rocky planets and outer gas giants, was born from such a disk. The very atoms that make up our bodies were once part of this cosmic dance, forged in the heart of a dying star and scattered across the cosmos. From the smallest grain of dust to the largest gas giant, every object in our solar system owes its existence to the processes that unfold within these protoplanetary disks. It's a humbling thought, isn't it, that we are all connected to this grand cosmic narrative. Now let's journey into the protoplanetary disk, a swirling chaos of gas and dust. Here, under the watchful gaze of the newborn star, the process of planet formation begins. Imagine a dance floor filled with countless tiny particles, all moving and swirling in a mesmerizing ballet. These particles, grains of dust and ice, are the building blocks of planets. But how do these tiny particles go from dust to planets? It all starts with a simple yet profound process called accretion. As these dust grains collide, they stick together, drawn by electrostatic forces. Think of static cling, but on a cosmic scale. Over time, these tiny clumps grow larger, forming pebble-sized grains. These pebbles, in turn, collide and merge, forming larger and larger objects. As the clumps grow, their gravitational pull increases, attracting even more material. It's like a snowball effect, but instead of snow, we have dust and ice. And instead of a gentle slope, we have the immense gravity of a protoplanetary disk. These growing clumps, now boulder-sized and beyond, are called planetesimals. They are the planetary embryos, the seeds of planets destined to become the planets we know and love. Think of them as the rebellious teenagers of the solar system, jostling for position, their paths crossing in a chaotic dance. Within the protoplanetary disk, there are millions of these planetesimals, all vying for material. Some will grow to become planets, while others will remain as asteroids, forever frozen in time, remnants of this early era of planet formation. The next time you look up at the night sky and see a shooting star, a tiny speck of dust burning up in our atmosphere, remember that you are witnessing a fragment of this ancient process, a tiny piece of a planetesimal that never quite made it to planethood. Chapter 3: Planetary Collisions and Growth. As our planetesimals zoom around the protoplanetary disk, their increasing gravity turns them into cosmic vacuum cleaners, gobbling up anything in their path. Smaller planetesimals are drawn towards larger ones, their collisions releasing tremendous energy. Imagine the early solar system as a cosmic billiards game with planetesimals as the balls, their collisions shaping the destiny of planets. Some collisions are glancing blows, altering orbits and sending objects careening off in new directions. Others are catastrophic, resulting in the complete obliteration of one or both objects. But it's from these violent collisions that planets truly begin to emerge. When two large planetesimals collide, their combined mass and gravity increase dramatically. This allows them to pull in even more material from the surrounding disk, accelerating their growth. One of the most dramatic examples of this process is thought to have occurred right here in our own solar system. Scientists believe that a Mars-sized object, which we call Theia, collided with the early Earth. This cataclysmic event ejected a tremendous amount of debris into space, some of which eventually coalesced to form our moon. As protoplanets continue to grow, their gravitational influence shapes the surrounding disk. They carve out gaps in the disk like grooves in a vinyl record, clearing their orbital paths and gathering up any remaining gas and dust. The fate of a protoplanet depends largely on its location within the disk. Those closer to the star, where temperatures are higher, will primarily accrete rocky material, forming terrestrial planets like Earth and Mars. Those farther out, beyond the frost line where temperatures are much colder, can hold on to lighter elements like hydrogen and helium. These protoplanets have the potential to become gas giants like Jupiter and Saturn, their immense gravity drawing in vast amounts of gas from the surrounding disk. Chapter 4. Planetary Evolution and Stabilization. Over millions of years, the once chaotic protoplanetary disk begins to settle down. The central star, now in its full glory, bathes the system in light and heat. The planets, having cleared their orbital paths, settle into more stable orbits. The type of planet that emerges from this process depends on its location and the materials it has accumulated. Close to the star, where temperatures are scorching, rocky planets with thin or no atmospheres prevail. These planets, like Mercury, Venus, Earth and Mars, are forged in the crucible of intense heat. Farther out, beyond the frost line, gas giants reign supreme. Jupiter, the largest planet in our solar system, is a testament to the immense size these behemoths can attain. Saturn, with its stunning rings, is another example of a gas giant, its composition reflecting the icy materials present in the outer regions of the protoplanetary disk. Between the rocky inner planets and the gas giants lie the ice giants, Uranus and Neptune. These planets, though smaller than Jupiter and Saturn, are still significantly larger than Earth. They are rich in ices, not just water ice but also methane and ammonia, which gives them their distinctive blue hues. As planets evolve, their surfaces and atmospheres undergo dramatic transformations. Volcanoes erupt, spewing molten rock and gases into the atmosphere. Oceans form, their tides sculpted by the gravitational pull of the star and nearby moons. The early Earth, for example, was a hellish world of molten rock and constant bombardment from asteroids and comets. Over time, however, our planet cooled, allowing liquid water to condense and form oceans. The emergence of life on Earth is a testament to the incredible resilience and adaptability of nature. Chapter 5. Can life begin? The formation of a planet is a remarkable feat of cosmic engineering, but the story doesn't end there. The question that has captivated humanity for centuries is whether we are alone in the universe. Does life exist beyond Earth? The answer, at least for now, remains elusive. But we can look to the process of planet formation for clues. We know that life as we know it requires certain ingredients: liquid water, a stable atmosphere, and a source of energy. These ingredients, while seemingly simple, are the result of a complex interplay of factors. The habitable zone, the region around a star where temperatures are just right for liquid water to exist on the surface of a planet, is a key concept in the search for life. Planets in the habitable zone are neither too hot nor too cold, making them prime candidates for hosting life. But the habitable zone is just the beginning. A planet's atmosphere plays a crucial role in regulating its temperature and protecting life from harmful radiation. Earth's atmosphere, for example, acts like a blanket, trapping heat and keeping our planet warm enough for liquid water to exist. The presence of a magnetic field like the one that surrounds Earth can also be a major factor in a planet's habitability. Magnetic fields act as shields, deflecting harmful charged particles from the star and protecting life on the surface. The search for life beyond Earth is one of the most profound scientific endeavors of our time. By studying the process of planet formation, we gain a deeper understanding of the conditions necessary for life to arise and the factors that make a planet habitable. And who knows, perhaps one day we'll discover that we are not alone in the universe. Perhaps on a planet orbiting a distant star, life has taken hold. its own unique story unfolding on a world shaped by the same cosmic forces that gave birth to our own. Thanks for watching. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more fascinating content about our universe. From the swirling chaos of a protoplanetary disk to the elegant dance of planets in orbit, the formation of a solar system is a testament to the awe-inspiring power and beauty of the cosmos. Keep looking up, keep asking questions, and never stop exploring the wonders of the universe. See you next time.